we're going to shift away from muscle cells, identifying the histology. We saw last time how we make muscles contract and move. But of course, to make muscles move, and for one cycle of our cross bridges, from where we're starting, when we get our power stroke and we reset, how many ATP are used per cross bridge cycle? 2. You preload with one, and you have to have the second to release and reset. So a muscle contraction involving many cross bridge cycles uses a lot of what? ATP, or energy. And so to produce energy, we are going to use a lot of fuel. And in fact, when you look at your muscles at rest have stored enough ATP, have stored enough energy to last about 5 or 6 seconds. We have a couple of decathletes, right? Is there an event that only lasts 5 or 6 seconds for you guys? No, pretty much. So you're going to be out of energy pretty much at the gun, just as you get started. So we have reserve sources of energy, and we have fuel with which we can continue to make ATP. Now, we talked about metabolism a little bit. We're going to get into it again here and put it to good use. But what 2 ways does our body have to make energy? With or without oxygen. What are those 2 names? Aerobic and anaerobic respiration. That's the way we take our fuel and we produce more ATP. Now we're going to see whether it's with carbohydrates, whether it's with fatty acids. We can even, in fact, begin to break down proteins so that we can have more ATP, so that we can have more muscle contractions. It's all about the energy. And so we're going to be looking at metabolism of muscle today. How do muscles provide the energy necessary to accomplish what is being asked of them? Because rather than sporting events, athletic competitions, our muscles are used for survival. In the animal kingdom, that's what it's all about. Finding food, finding a mate, and to prevent you from being someone else's meal. So you have to have those energy reserves to keep your muscles contracting. Is anyone surprised to hear that aerobic respiration is the principal process with which our muscles are provided energy? Why would you not be surprised about that? When you look at aerobic versus anaerobic respiration, where do you get more energy out of your glucose? Which one? That's aerobic, right? That's a no-brainer. We get 38 ATP out of the glucose. If we look at anaerobic, do you remember another name for anaerobic respiration? We don't produce a lot of ATP, but we produce lactic acid. Do you remember that pathway? It's called fermentation. You don't have to have oxygen, but you produce far fewer ATP. So as we're reminded about our formula for aerobic respiration, we produce 38 ATP. But here's the problem with aerobic respiration. It's kind of slow. We didn't go through all the steps of aerobic respiration, did we? No, there are a lot of them, a lot of intermediates. Then we get into glycolysis, Krebs cycle, oxidative phosphorylation, electron transport. It takes a lot of time. But kind of a cool thing about it is we focus on glucose. Glycogen, remember, is the storage form of glucose. But any place along our chemical reactions of aerobic respiration, we can also plug in triglycerides. We can also plug in amino acids from proteins. And so it's a very efficient means, a very versatile means of producing a lot of energy, but it's slow. It takes time. Now, we also know that a limitation of aerobic respiration, as the name implies, you've got to have what? Oxygen. Do you remember why we have to have oxygen? What is the role of oxygen? Does oxygen play a role in glycolysis? No. Does it play a role in the Krebs cycle? No. Oxygen is that very last thing, remember? Oxygen is the electron acceptor at the end of the electron transport chain. And it's bundled with hydrogen to produce water to keep the electron transport chain going, which keeps the whole process moving so that you can continue to produce more and more ATP. So since this is a slow process, and since your muscles only have about 5 to 6 seconds worth of energy stored, that's why there is a special protein that is present in muscle. And that protein is called myoglobin. Now, you've all heard of hemoglobin, right? Have you heard of myoglobin before you were either in here or in lab? It's a storage form of oxygen that's present in the muscle because myo is a prefix that means what? It means muscle. So as oxygen is transported in the bloodstream, that oxygen is going to be transferred to the muscle. And if the oxygen is not immediately used for aerobic respiration, then that oxygen is going to be bound to myoglobin and stored in the muscle. And it's one of the reasons why our muscles appear red. They're often colored red. And that's why in a couple of weeks, when you sit down at the table, typically you're going to be asked, what kind of turkey do you want? And what are your two options typically? White meat or dark meat? The dark meat is dark because of myoglobin. Because of myoglobin. It provides an oxygen reserve when the muscles run out of that ATP after 5 to 6 seconds. So as we begin physical exertion, and our muscles burn through very rapidly those 5 to 6 seconds worth of ATP, the metabolic rate is going to jack up 20-fold. Your muscles are going to be working. Metabolizing, aerobic respiration, producing more energy. But often, when you are doing something strenuous, the demand for energy is going to exceed the oxygen supply. And then we have a few options. Once we exceed the oxygen demand, the efficiency of our work, the efficiency of our muscles, the efficiency of the homeostasis of our body is going to decline rapidly. And we're on a limited timetable until we're basically out of gas. When you run out of energy and you build up a certain level of these byproducts in your bloodstream and in the muscles, lactic acid being one of them, your muscles are just going to stop. They're going to fatigue and they're going to say, I don't care what you think, I'm done. Most of us will never get to that point. I am not mentally tough enough to get beyond that point. And most of us aren't. So we're going to look now at how do we restore, how do we produce that ATP for our muscles even when and if oxygen is in very short supply. So we're going to look at a couple of different systems. This first system is called the phosphagen system. This is a system in which you are not going to basically produce and store more energy. But you are, in fact, going to move phosphates around. And you're going to liberate the energy in these chemical bonds of the phosphates and move them from one molecule into ATP. And so this is going to be utilizing creatine phosphate. And with creatine phosphate, when ATP is in short supply, meaning when you are undergoing a lot of strenuous activity, burning through that energy, remember ATP is converted into ADP? So you've got a lot of ADP, this empty debit card. Well, in those situations, creatine phosphate is going to transfer this phosphate and the chemical energy of that bond. It's going to be transferred to ADP, and you're going to create ATP and a molecule creatine. And so now we've got a molecule of ATP that we can use as energy, but we didn't have to go through aerobic or anaerobic respiration. The advantage of not having to go through these metabolic steps is it's extremely rapid. But this doesn't happen on its own. This is going to be facilitated by an enzyme. And when an enzyme adds a phosphate, what kind of enzyme are we always talking about? A kinase. Kinase adds a phosphate. A phosphorylase removes a phosphate. And in this case, it's got a cool name, creatine kinase. Because creatine kinase, in this case, can add a phosphate to creatine. And in this case, the kinase is removing the phosphate from creatine and it's adding it to ATP. So this kinase actually is multi-talented. We're focusing on what it does after it removes the phosphate from creatine. Now, how long did we say we had ATP stores for our muscle to start with? 5-6 seconds, right? The phosphagen system is going to add about another 10 seconds. So, 100 meters, you got 15, 16 seconds. Is that going to be enough? Are we good? Is that one of the decathlon? So 100 meters, we got that. We don't have to worry about providing any more ATP. That's what we have to do. That will see us through. But let's say we have to do something that takes longer than the 15 to 16 seconds. We need more energy. Well, we can invoke this myokinase system that's similar. The phosphagen creatine system gives us about 10 more seconds using creatine phosphate. This one I think is even cooler. Again, I think this goes back to big brother, little brother kind of concepts. Because when you're burning through energy, you're using the link of the phosphate on ATP, adenosine triphosphate. What does that mean you're going to have a lot of in the muscle? ADP, right? And what does ADP stand for? Adenosine diphosphate. If you have a lot of diphosphates, are you sort of figuring out where we're going here? Okay, you got 2 phosphates, I got 2 phosphates. How can we get together and end up with 3 phosphates? Right? 2 ADP come together, and I don't know how they agree on who's going to give up that phosphate, but somebody gives up a phosphate so that now we have ATP and adenosine M. What's the N stand for? Monophosphate. Again, another system in which we didn't require oxygen, we didn't require a lot of metabolic steps, but again, here's another kinase that's allowing us to add the phosphate to ADP. And this gives us another 2 to 3 seconds. So we're getting close to 20 seconds worth of activity. And we haven't had to metabolize anything else. So we're still in this stage of what we're referring to as a sprint. All out, everything you got, not pacing yourself, not holding anything back. 20 seconds worth of activity. We can account for that. Have you ever had to do something, exercise, activity that lasts longer than 20 seconds? Most every day, right? You have to walk up from the commuter lot. That's going to take more than 20 seconds. So in that case, if we must continue for longer than 20 seconds, now we've burned through our ATP, our stores of energy in creatine phosphate. ADP has given us a couple of more seconds, and now we're like, okay, we need something in a hurry. And this is where our anaerobic respiration comes in. The lactic acid pathway, and there's that word fermentation. Now, when you hear fermentation, what are you thinking about? Beer, alcohol, right? Some of you may have experimented with that this weekend. But understand fermentation is the metabolic process of essentially producing energy without oxygen. And so as we look at this lactic acid pathway, we're going to have a lot of glucose. Why do we need more glucose for fermentation than we do in aerobic respiration? How many ATP do we net in fermentation? 2. What do we net in aerobic respiration? 38. So if we're going to produce the same amount of energy, we're going to need roughly 16 times more glucose for fermentation than we would use through aerobic respiration. So we're going to store a lot of our glucose in our muscles because that's where we're going to use them, but we can also store a lot in our liver. And what is our storage form of glucose? Glycogen. What hormone is released from the pancreas that causes glycogen to be broken down into glucose? Glucagon. Again, we remember the insulin part, but the opposite, so we're just continuing to talk about that. So, 20 seconds in, we burn through our energy. We're working harder than we're bringing in oxygen, so anaerobic respiration kicks in. It kicks in after we use it up because it's slower than we saw with the phosphagen system, with the myokinase system, because there's one enzymatic step in those. Even for lactic acid, there are 12 chemical steps. So even if they got started at the same time, and most of these do, most of these processes overlap, it still takes time to begin to produce the ATP that we need. Principally because it's slower and it's not very efficient. But which is better, 2 ATP or no ATP? When you're running for your life, 2 is better than nothing. It's the bottom line. But the downside of this emergency system, that's sort of how I look at fermentation. Because if you're running faster than you can catch your breath, and yeah, this is an emergency. And the trade-off is there's going to be pain, there's going to be fatigue, because your blood pH level is going to plummet in a hurry because of lactic acid, that toxic byproduct of breaking down glucose. And so because it's slower, because it's less efficient, and because of the buildup of lactic acid, your muscles are only going to agree to do this for about 1 to 2 minutes. So now we're up to 2.5 minutes worth of activity. Anything that we do takes longer than 2.5 minutes? Quite a bit. So now we either have to change something or your body's just going to quit. Your body's just going to give up. Because we can't continue with this level of exertion and this level of activity. So this is where your brain and your body says, I'm not doing that. I'm not running that fast anymore. I'm not. I'm either quitting or you slow down. So we got the 100 meters. What's the longest? 1,500? How long does that thing take? About. Not how long it would take me. It would take me a day. 4.5 minutes. Running for 4.5 minutes. Once again, if you see me running, call 911. So if you know you're going to have to run for 4.5 minutes, do you come out of the block sprinting? If you want to position yourself somewhere, if you want a certain lane, maybe, but you don't keep that pace the whole 4.5 minutes. You can't. So, for prolonged activity, you have to slow the pace of your muscular exertion. Why? Because your demand for energy cannot exceed the supply of oxygen. And as long as you keep that level of activity down, the burning of oxygen does not exceed the supply of the oxygen. We were at 2.5 minutes before. Look at our marathon runner. Unlimited amount of time. That's where your body can just keep going and going and going, and it becomes a mental issue at that point as far as running and your level of activity. So let's put this all together. When you look at this graph, we can see in yellow, this is the ATP stored in your muscle initially. Boom. 5-6 seconds, we've got it down to about 2. But as we're burning those initial stores, here we can see the phosphagen. Okay, that's going to be our creatine phosphate or phosphocreatine system there in purple. Do you see how they overlap? This one's coming on as we're burning that ATP so that we don't have to burn through all this and then wait for more to be produced. We're going to be burning through some of that creatine phosphate as well. Now, as our aerobic system is getting ramped up, here is our anaerobic system clocking out. We're going to clock that out here at about 1 minute. And then we've got our prolonged activity. Now, this line that you see, this is our overall performance. And again, you may have sprinted out of the blocks. You may have sprinted around the first turn. But now, you're in that 4 minutes worth. And so your performance has to level out. And you're hoping that you're not burning through oxygen so fast that you're not going to have something left for the home stretch, where you got to kick it in. Then you're going to try to regain some of this for that last sprint to the finish. Now, here's the other thing I want to point out. Now, can we all say, not just picking on our track athletes, but have most of us done something like run at some point in our life? Whether it's competitive, whether it's chasing your brother or sister, or whether it's you're running from your brother or sister, we've all done this. Have you ever noticed when you first start running, you're not breathing hard? You ever notice that? You're not breathing hard. Does this graph help you understand why initially you're not breathing hard? For the first minute, 2 minutes, what are you not needing any more of? Oxygen. That's why when you first start running or exercising, you're not breathing hard. But then if you continue that level of exertion, you're going to start breathing hard. You're going to feel it. You're going to notice your respiration. But here at your sort of leveled out performance. You can judge your exertion by your respiratory rate. And if you're breathing normally, if you're breathing naturally, you're going to feel more energized. Your pace is going to be more steady. And you're going to know at that point your oxygen supply is enabling the work to happen. You haven't exceeded that. But here's the thing. During this level of performance, you're not really building all this up. You're essentially burning the fuel as fast as you make it. You're just not burning the fuel more quickly than you make it. But you're still supplying the oxygen. Now, we didn't start breathing fast, right? Until kind of into the race. Does this look familiar to anybody? How many athletes do you see in track cross the finish line and collapse? How many times have you been running, whether it's on a treadmill, whether it's on the stair climber, something aerobic, and when you finish, typically when you finish exercising, what do they say, what kind of period do you need after? Cool down period? You ever heard cool down period? Have you noticed when you stop running, when you stop pedaling, you're still breathing like crazy? I mean, you're not working out anymore. Why in the world are you still breathing like you are? You ever wondered that? Well, because you've burned through your stores of ATP, because you've burned through your stores of creatine phosphate, because you've burned through a lot of your ADP, you have an oxygen debt. Those stores of energy that are going to allow you to have that 2 minutes or so of energy without oxygen have to be replenished. And the way it's going to be replenished is basically by you bringing in that oxygen. The oxygen you breathe in during your cool down period is going to be to replenish your myoglobin and your hemoglobin. Get the oxygen back in the blood, get it back into the muscle. During your cool down period and right after, we're going to start putting back the glucose that's now in our bloodstream that we're not burning through as quickly. We're going to put that away. It's like you bring all the food out, you make a meal, and then you put it away, the leftovers. We're putting the leftovers back in the fridge. That oxygen is also going to be to build up our 5 to 6 seconds of ATP, store it. That oxygen is going to help us to load up creatine back to creatine phosphate, which is going to provide us another couple of seconds. And in fact, that cool down period is important because that's going to help us take the lactic acid. And one way we can remove lactic acid from our body when we're not requiring a ton of energy is to convert it back to glucose. Remember, we're one step away. We're one step away. Because we took that pyruvate, instead of plugging it in to our Krebs cycle, we just burn it in one step. Got those 2 ATP. And so taking lactate, putting it back to glucose is called gluconeogenesis. Neo is new, genesis the formation of. So it's the new formation of another molecule of glucose. Now, when we look at glycolysis, what do we say our net ATP was for fermentation, which is basically glycolysis, was 2. So do you see now, to build glucose up from lactate, we're going to lose a net of 2. So we've got to have ATP. We've got to have oxygen. So once again, all these things are happening while we're cooling down, while we're replenishing our oxygen debt, so that we can do something active again as quickly as possible. So if you ever see me in the gym, and you see me lifting weights, and you see me sitting on my backside, do not come up to me and say, Oh, what are you doing? Are you resting? Sure taking a long time between sets. Big guys love to do that to me. I don't know why. Pick on me because I'm old and little. Because you know what I'm going to tell you? Say, I'm not. I'm replenishing my oxygen debt. Back off, man. I'm a scientist. Right? So, coach says, why are you resting? Coach, I'm replenishing my oxygen debt. He'll probably make you run more if you say that. But anyway, I wouldn't try that at home. Any questions? So when you look at a graphic that basically illustrates our oxygen debt. So here we are before we start. Here's our level of exercise. Now, if this was a perfect world, does anyone wish it was a perfect world? If it was a perfect, it wouldn't be fun. Come on. If it was perfect, it wouldn't be fun, exciting. But in a perfect world, your level of activity would be this dotted line. If you're working hard, boom, you're going to supply enough oxygen. You're going to keep supplying enough oxygen. You're done exercising. Your oxygen's done. You walk away. No sweat, no heavy breathing, right? Good day. No, it's not how it works. After we burn through our first ATP, then we slow down the ATP production, burning our oxygen. This portion of our scale, that's our oxygen deficit, the oxygen debt, what we've borrowed against. And if you haven't figured this out with your credit cards, because I'm sure that one of the first things in college they hit you up with is, get our credit card, get our credit card. Look how much you can have. Look at your credit limit we're going to give you. You don't read a small print on the back where it's 38% interest, do you? Until it's too late. Because just like putting stuff on a credit card, you got to pay that business off at some point. You got to pay it back. And where you pay it back is at the end where you begin to pay off your oxygen debt that you occurred in the beginning and during that time. And that's where our cool down period, that recovery period, is important. Now, in going through and looking through this, we've talked about the fuels. I mean, this is how we burn it. This is how we metabolize our stores. This is how we produce the energy, the ATP. But we've got to have stuff to burn through, right? We've got to have the fuel. And just as there are various steps that our body will utilize from a metabolic standpoint as our energy level and exertion goes up, our fuels change as well. And so when we look at our fuels, we're going to see that we have fuels that are present in our serum. Are we good with what serum means? Another word for serum would be plasma. This is the liquid portion of your blood. And so in the liquid portion of your blood, we have free-floating glucose and we have free-floating fatty acids. Fairly immediate sources of fuel that we can burn during our aerobic respiration. Or if it's glucose, we can burn through that with fermentation as well. Fermentation's not going to burn through our fatty acids. But as we increase our activity, as we prolong this activity, especially if the intensity increases, now we're going to start burning through our stores of our triglyceride, which is fat, and then we're going to burn through our glycogen stores. So the metabolism is the fire. This is the fuel, the wood that we're putting on that fire. And we don't necessarily burn them all at the same time. Much like we saw, our ATP stores are first, our creatine phosphate is next, anaerobic is third, and then aerobic sustains us. We're going to see that with these 4 different sources of fuel, they're burned at different times. So let's look at this top graph first. This is your effort, all right? 100% is max effort. 0% is what I like to do, watch TV. And so as you increase your activity level, and notice we've got mild, like warm-up exercise, moderate exercise like most of us probably do. That's what we call exercise. And then your high intensity sprinting heavy exercise, that's going to be over here on the far right. For 30 minutes worth of that activity, the first thing you're going to burn through is your plasma glucose. And then in yellow, we're going to burn through our plasma fatty acids. So this is the fats that we don't like for cosmetic reasons, that are in our blood but are going to be stored in our adipose tissue if we don't get rid of it. But as our intensity increases, we burn through that fairly quickly. Now we're going to start recruiting the storage form of fat, that triglyceride in our muscle. And after that's gone, now we're going to dip into our glycogen, that storage form of glucose. Now, I know a lot of distance athletes. I think cross-country folks do this a lot. They may have you guys do this. Do they carb load you the day before or so? Have you ever heard of carb loading? I guess about 24 hours before, you eat a meal rich in carbohydrates so that you can load up this purple box. Because the next day at the meet, you're going to be dipping into that. And you don't want to go into the cupboard, open those doors, and you not have enough fuel to finish the race. Have you ever done that? You got roommates, right? Have you ever been thinking about that chocolate Pop-Tart? I know there's that pack of chocolate Pop. I want that pack of chocolate. And you go to the cupboard and open it and your roommate ate it. Does that ever happen? Happen to anybody else? I heard no. Do you not eat Pop-Tarts? No, I remember in college, I would hide stuff under my bed. I wouldn't put it in the kitchen where they could find it. No. So you store it because you're going to have to use it. Now, let's look at the bottom graphic. 90 to 120 minutes of activity. Notice we don't have the heavy exercise scale. You're not going to sprint for 2 hours. So that's not going to happen. But when you look at mild exercise over the course of that 90 to 120 minutes, what are you principally burning through? What fuel are you mostly using? This is going to be the fats in your serum. And even if you get to moderate exercise, you're really burning through that serum fatty acid. So what's the take-home message from this? If you're going to run a marathon, carb load. Yeah, that's one of them. The other message, if you're just that typical person that goes into the gym and you're wanting to maintain, or maybe you're wanting to lose fat, lose weight. When you get in the gym, and you've seen these folks, right? Have you seen the folks that they are decked out in the latest wear? They have all the logos on everything? Brand new, maybe they still got the tag on their pants. And they'll get on the bike or they'll get on the Stairmaster and they will absolutely go nuts. 10 seconds and they're like, okay, boy, that was good. Done. Have you seen those folks? What are they doing? Nothing. Letting you see them in the gym. You don't have to go kill yourself. If you're wanting to lose weight, if you're wanting to burn fat, lower activity level for longer period of time. That's why a lot of people say if you're not used to working out, if you're not used to exercising, what's one thing that you can do and should do? Walk. Just walk. But don't think you're going to walk for 5 minutes and change your lifestyle and change the way you look and the way you feel. Because it's all about the metabolism and it's about what fuels you're going to use to make that happen. Does everybody see that? So again, maybe you think, well, I can't go, run, a 5-minute mile. I can't do that. I can't go get on a bike and, ride 20 miles in 10 minutes. Not many of us can. But you don't have to make a difference in your health and fitness level and the way you look and feel about yourself. Mild exercise, longer periods of time, it's going to accomplish quite a bit for your body. It's going to burn a lot of calories, more than I think you can imagine. It'll burn through. Now, we've talked about our 3 types of muscle, right? What are our 3 principal categories of muscle? Skeletal, cardiac, and smooth. Have y'all got to all those in lab yet? Okay. So one of the last things I want to cover today is this whole idea of muscle fiber types. Now, again, skeletal muscle, you may be thinking, well, isn't skeletal muscle, isn't it the same thing? But it's not. And when we talk about fiber types, remember, we're not talking about a whole muscle. We're talking about a muscle what when I say fiber? Cell. So we have different types of skeletal muscle cells. And we can categorize them in a couple of different ways. One way is, well, how fast do they contract? And in that case, we can have fast versus slow. They put twitch on here because of sort of the piston activity of our cross bridge cycles. So fast versus slow twitch. Fast twitch fibers. These are going to provide much greater power, much more rapidly. Slow twitch fibers, as the name implies, are going to be slower. And what I would like for you to write in here, there's no space there, but what I want you to write in there, greater endurance. The fast twitch, yeah, they're powerful, they're fast, but they're not going to last long. This is like, you remember the story of the tortoise and the hare? This is the tortoise, that's the hare. The hare's going to go real fast, but it's not going to make it to the finish line because it's run out of gas. Tortoise is going slower, and it can go all day long past the finish line. It just takes longer to get there. These are the sprinters. These are the distance runners. They're not going at the same pace as these guys are, but they can go a lot further. So contraction rate, one means in which we categorize our skeletal fibers. Another means in which we can categorize these is based on how do they supply sufficient ATP. So in one sense, we have oxidative fibers. And as the name implies, oxidative, these are going to be fibers that principally use aerobic respiration. Now we said aerobic respiration was typically how we supply ATP to our muscles, but that's going to be the slowest. You remember our chart? That's the last one to really get ramped up and going because of all the steps in the chemical reactions. So oxidative is going to be slower, but what benefit do you have? Longer periods, greater endurance. And when you look at those oxidative fibers, you're going to have a lot of capillaries. Why do you have to have a lot of capillaries going to the muscle? What are the capillaries bringing in? Blood, but typically what's going to be coming with the blood? Oxygen. You're going to have a ton of mitochondria. What do mitochondria use to make energy? Oxygen. You need a lot of oxygen in your muscle, so you have this guy, myoglobin. Myoglobin binds to what? Oxygen. You see, it's all about the oxygen. And when oxygen binds to myoglobin, much like when oxygen binds to hemoglobin, what color do you get? Red. That's why your muscles, many of them are red. Now the other type of fiber, these are going to be the ones that undergo anaerobic. They provide some power fairly quickly, but they're going to not give you the endurance that you get with the oxidative fibers. So in this sense, We don't have a lot of capillaries there. We don't have a ton of mitochondria. But the one thing that you do have in these glycolytic, what is lytic lysis? What does that mean? You remember that word? Break. Glycolytic, breaking glucose. And we're breaking glucose down into lactic acid. You're going to have a lot of glycogen stores in these glycolytic fibers. Not a lot of myoglobin. And so these are going to be white in appearance. So you'll hear talk about fast twitch, slow twitch, and red and white fibers. And when you look at a particular section of skeletal muscle, you're going to see all three fiber types. And the predominant fiber type in that muscle is going to dictate the performance of that muscle when it's subjected to strenuous activities. Now, you don't have to memorize this chart. This chart basically is summarizing what we just talked about. Just wanted to point out a couple of things on the chart. First of all, this slow versus fast twitch, that relates to how fast can you produce ATP and use the energy in the head of myosin. Remember that myosin head binds to the ATP and then breaks it down to ADP and phosphate? If you can break ATP down faster to release the energy, you can have more cross-bridge cycles. So that's going to supply our slow versus fast twitch. We talked about endurance, oxidative fibers, going to be slow, fatigue resistant. Our glycolytics, those are going to be fast and burn through quickly. Here's our myoglobin content, and that directly relates to the color with which you see in the fiber itself. And much like we saw with our metabolism, we started with our ATP stores, then we went to creatine phosphate. When you look at getting work done, you're first going to start with slow oxidative. If they're not enough, we're going to go fast oxidative. And if we still need more to get the work done, then we recruit our fast glycolytics. So again, there's a sequential nature to the fuels that we use. There's a sequential nature to the metabolism that these cells undergo. And there's a sequential nature to the fiber types that are used to accomplish the work.